Hey you guys, this is Mr. Sal. We're going to look at 4.1, solve systems of equations by graphing. Thanks for watching. Don't forget to like, subscribe, and comment about the lesson below. Systems of equations are great because if you didn't get enough of one equation, systems of equations have two equations. Well, just for this class we have two. Eventually you can have like 5 or 6 or whatever, but we're just looking at two equations for now, because the most we deal with in this class is two variables at a time. One of those methods for solving them is by graphing, which up until 4.1 is your favorite. Sometimes when we get to 4.2 you forget about it, and that's okay too. But for now it's your favorite because it's the only one we have. The solution to a system of equations, whether it's graphed or solved by any other of the methods that we will look at, is always the point of intersection between two lines. Now we're only dealing with straight lines, so if this was our line, that's a little big, like this one, and then we had this red line. Now we're not going to figure out exactly what that value is, but the point where those two lines intersect is the solution to the system of equations. Keep in mind, though, now this kind of goes back to the definition for solutions, is if I for some reason thought that this was the point where those two intersected. That's very easy to see on a graph. However, when we start getting to not graphs, then we will see perhaps in the red equation I would find that the blue dot would give us truth. But for the purple line, since it's not on the purple line, it would give us falseness. Now yes, this is leading up to something bigger, because if you guys will check your work, you can know for certain that an answer is correct or not, if you just check. But usually only 1 or 2 students will. You guys have been different though, you guys have been great. Determine whether each given ordered pair is a solution for these systems. Now this means, and this would be the point where we have graphed it, we found the point of intersection for the two lines, and we're just seeing if it is true for both, which would confirm that it is the solution to the system. So we'll say maybe this one would have been the red one, right? So I got x minus y equals 3, but I have values for x and y, 4 and 1, so we'll replace those in the equation. And when I solve this, again, we're looking for truthfulness here. 4 minus 1 is 3. 3 does equal 3, that's true. So I can move on to the next equation to see if that is true. Now let's say that was a green line, and we can do it in green or whatever. If that first one was false, there's no need to check the second one, okay? Because it means that whether it's true or false, it's still not the solution to the system. But that one was true, so we'll continue on with this thing. And once again, we have our x and y values at 4 and 1. And then we'll solve this. 2 times 4 is 8, minus 3 times 1. Yeah, we're checking to see if that's true. Is 3. 8 minus 3 is 5, which does equal 5. So this one also is true. Since both of these are true, this one is a solution to the system. That's a bad yes right there. Let's try that again. I feel better about that one. Yes. Let's try the next one. So we're testing negative 3, 3 to see if it gives us a true statement for both equations. If it's false, then we know that it's not the solution. So we'll try this one in red again. But we'll replace the x and y values with their respective values of negative 3 and 3. All right. Well, let's just see if this is true. 3 times negative 3 is negative 9 minus that 3. Does this equal negative 12? It does. So this one is true, which means we need to check the next equation. This one's a little bit easier. X minus y equals 0. But we're testing these values, negative 3 and 3, to see if it is a true statement. X is negative 3, y is 3. Now you got to be careful on this, because if you just kind of breeze through this thing, you're gonna say, yeah, that's true. However, that's negative 3 minus 3, which gives us negative 6, which does not equal 0. That is false. So this one is a no. I don't know if we need the exclamation point. Now once again, since this is something that you should do on a test, if you did this and you said, yeah, the first one was true and the second one is false, you don't have to feel bad inside, okay? It just means that you should feel really good inside, because now you know that if you leave it that way, it's going to be marked wrong. But you can go back and fix it, which is great, because, I don't know that we get too many opportunities to do that during a test. So in Module 3, we learned how to graph equations. These are standard form equations. So we could use a table, or we could change these into slope-intercept form and graph them. But I'm going to let you guys choose. You tell me which one you want. Slope-intercept it is. So I'm going to start with this x minus y equals 2 equation. And we'll solve this, or manipulate it for y. So I'm going to subtract the x from both sides, because that is a positive 2. And that's really negative 1y, so I'm just going to divide all the terms by negative 1, which really is just going to change the signs on that. So my red equation would be y equals, that's now a positive x, and that's now a negative 2. Y equals x minus 2, and if it does help, we can show the coefficient of x is 1 over 1, so we can follow along with the slope on that. Now from this I've got a y-intercept of 0, negative 2, which allows me to put that point on the graph. And from this I'm going to go up 1 to the right 1 for my slope, right? So up 1 to the right 1, and that gives me this point right there. And I can continue this pattern of stair steps until I get to the edge of this thing. That's a long ways. And just like we did before in Module 3, we can continue this pattern to the left. And that would be the line for the red equation there in the box. I'm not going to draw the line through the points. The reason is because, well, I'll do that later actually. But I want to see where these two lines intersect. And right now we're not going to give you guys any funky values that you kind of have to estimate on these yet. Now we'll look into fractional values, but that's a different technique. Now the next one we'll do in purple here. So you guys like that slope-intercept form stuff, so I'm going to change this into slope-intercept form. We'll have to subtract x from both sides to start. And from here we'll divide all the terms by 3. So that gives us just the y equals, we'll make that a negative 1/3 x. And 6 divided by 3 is 2. So there's my purple equation, which has a y-intercept at 0, and this is positive 2. Right there, that's good. And my slope, I'm going to reassign that negative to the 1, which means it will be down 1 to the right 3. Down 1 to the right 3. Bam, we nailed it. Of course, there was a lot more red points than we needed, but it's just in case, all right? Just to finish this off and make it look pretty, we'll put the other points on this thing. All right. Well, I can see the point of intersection is right there because it was both purple and red. And the value, or the coordinates of that point, appear to be 3, 1, which is the answer. And like I said, we're going to make this look pretty. So let's draw the lines here. All right, and again, we can see they cross at 3, 1. Now again, just to check, these ones aren't too bad because they're in standard form. So the first one in red, x is 3, y is 1, 3 minus 1 is 2, so that's true. The purple one, 3 plus 3 times 2, no, 3 times 1, I'm sorry. 3 plus 3 times 1 is 6, that's true. And sure enough, it checks out, just like we wanted it to. So the biggest difference between this one and the last one is that one of the equations is already in slope-intercept form, which is great. This one. Now, like we talked about in Module 3, if you want to make that a plus 0 right there, that's okay. The only reason we would do that is to acknowledge that the y-intercept is 0, 0, which allows us to graph this using the slope and the y-intercept. And yeah, the slope will make that negative 3 over 1. So down 3 to the right 1, down 3 to the right 1 gives us these points. And then going backwards, we get these points to the left as well. Again, I'm not going to draw the line yet because I just want to see the points. And the next line, which we'll say is the purple line, should intersect one of those values. Now, since we're graphing, I mean, we still need the graph, but you could technically test all 7 of those points in the purple equation to see which one is true, because only one of them will be true. But graphing this, I think, is a little bit easier. We'll use the table on this one just because we did slope-intercept form on those last 3. I don't know. We don't need all the values, but whatever. So let's start with the y-intercept where x is 0. So that would give us 2y equals 4. So divide both sides by 2, and then y is 2. So we have the point at 0, 2. 0, 2. So they're pretty close already. What if we tried, yeah, we can try x is 1 also. See what happens. So then we got 6 times 1 is 6, plus 2y equals 4. We'll solve this for y. So when x is 1, y is negative 1. That doesn't really help us. Well, let me try 2, and we'll see if this works. Okay, let's try 2. So we'll solve for this. 6 times 2 is 12, plus 2y equals 4. Solving for y, minus 12, negative 8 divided by 2. Y is negative 4. So 2 negative 4 is this one. All right, let me tell you guys the reason I was distraught on that last one is these two, the red and green one, are 2 apart. And then on this next set, they were 2 apart. That doesn't happen very often. However, the pattern was confirmed because the next one also was 2 apart. What that means is that they're always going to be 2 apart. Now this brings up a good question for us, and I'll draw the lines here. That's about as good as my iPad can draw them. But what do you guys notice about those 2 lines? These are parallel, and how often or when will 2 parallel lines ever meet? Never. Since the answer is never, or they will never intersect, this one has no answer, which on the homework comes out as a DNE does not exist, because these 2 will never intersect. Bam. I do want to point out, though, if we had changed that purple equation into slope-intercept form, we would have saw that the slopes are the same at negative 3, and then the y-intercepts would have been different. One was 0, and then the other one would have been plus 2, it looks like. So that would have been another way to tell that they're parallel. All right, this one, extremely generous. They place these in slope-intercept form for us. Now, unlike that last one, we can see that the slopes are different on this one, so there should be some type of intersection on this. So on this one, I've got a y-intercept at 0, negative 1, and we have a slope of down 2 to the right 1. So I got my point at 0, negative 1 here, down 2 to the right 1, down to the right 1, and so forth, okay? So that's that stair-step pattern, but I can continue to the left as well, and I get these points. Now again, I'm not going to put a line through it until later, so I can see where the 2 lines intersect. We'll do this one in purple. Y-intercept at 0, 2. Slope, I'm going to make it down 1 to the right 2. So 0, 2 right there, down 1 to the right 2. It looks like I chose wrong, because as I go to the right on this thing, the red and the purple line are getting farther apart, which means if I went to the right, which would be up 1 to the left 2, it would give me this point right here. Now we can see that they intersect there, but again, just for pure beauty, I'm putting the rest of those points on there. And we can see they intersect at this point, negative 2. Oh, that's a positive 3. Negative 2, positive 3. Bam. Solving by graphing. That first equation is in slope-intercept form. We just don't see the slope on it. Uh-oh. So on this one, we could rewrite it as y equals 0x minus 5, if it helps us, okay? But we don't have to. It just shows that the slope is 0, whereas the y-intercept is 0, negative 5. And some of you guys don't even need all this business to know that this is a horizontal line. And so we can just kind of draw this. Hopefully yours looks better. All right, in any case, no matter how bad my line looks, I'm not putting points on that because I know it's just all across that line, so we should see some kind of intersection along one of the coordinates that's going to give us whole values. So the next one we'll do in purple. There we go. And we've got a y-intercept at 0, negative 9, with the slope of down 2 to the right 1. So at 0, negative 9, down 2 to the right 1, that's off the grid right there. So I'm going to make this up 2 to the left 1 instead. Up 2 to the left 1, up 2 to the left 1. There it is, even though we can put all these other points on here. So we'll draw the line on this thing. And that's not great, but it's good enough to tell where that line intersects the red one, which is at negative 2, negative 5. Now just be aware, and we'll see this kind of on the next section, that the first equation told us that the y value is negative 5. And we can see in the ordered pair there, the y value is negative 5. So we could check, right? Well, negative 5 is negative 5, so the red one checks off. But the purple one, negative 2 times negative 2 is positive 4. Minus 9 is negative 5. So that one also checks off, which you should do whenever you can. I guess I should circle my answer too, right? More of this standard form business. So you guys want tables or slope-intercept form? Now remember, on the table method, we only really need 3 points. And that's what we'll do on this one, just to confirm the pattern, right? And it would allow us to draw the line, which on the homework is, you only need 2 points to do that. Whatever. But when we're doing it freehand, like you guys are going to have to do on the test, hopefully this would turn out to be a little bit more useful. So there's our equation. We're going to have a table for our line, x and y values. So again, I like to start with some kind of 0 value, even if it were the y, but x is going to be better because it has a coefficient that's not 1. So negative 2 times 0, 0, y is 1. Bam. And we could graph that point if we wanted to right now as the y-intercept. So I'm not going to do y is 0 because that gives us a fraction. So I'm going to use some other x value. We'll try something like 5 just to see what happens. Nope, I'm not going to, because that's not going to work. It's going to be off the grid, if I did that right. So we're going to say 3. I chose that randomly, okay? So that's negative 2 times 3 is negative 6. So plus 6, 7. 3, 7. Okay, so 3, 7, that's this point right there. And we'll try a negative value as well. We'll just do the opposite direction, negative 3. So negative 3 times negative 2 is 6. 1 minus 6 is negative 5. Negative 3, negative 5. So that confirms the pattern again. And we could draw the line. What the heck, let's do it. There's our line. Again, you'd only need 2 points on the homework, and it will graph it for you. Let's do the next one in purple. All right, so I will choose the next value of 0 again. So negative 2 divided by negative 2 is 1. Oh, we did it. Now, even though we found the answer on this thing, wait a sec. Oh, they might be getting something else. Hold on to that, okay? Let's try another value like 3, for example. 4 times 3 is 12. Negative 2 minus 12 is negative 14 divided by negative 2 is 7. Yeah, now I did choose that on purpose because of the way the equation's set up. Here's what we should notice, is that this value is the same as this one, and that feels good. However, because we did need to graph the two lines, we see that this value is the same as that one. What this means is that the purple line is also going to be the red line. So they coincide. It's the same line. Now, the solution to a system is where these two lines intersect. So the question isn't really for this one, where do they intersect, but how many times? That's infinite times, so this one has infinite solutions. I don't know, I may have spelt that wrong, but I'm not picky.